Hello everyone, welcome to the video lecture in BK Math YouTube channel. Today we are going to discuss about Fourier cosine and sine series. You remember last time we have been dealt with the Fourier series expansion of periodic function. We deal what periodic function is, and only periodic function can accommodate the Fourier series expansion. Non-periodic function would not be represented as a Fourier series expansion. We have not had last time. We didn't make more instances. Rather, you can consider this as an exercise to solve backed up the Fourier series expansion that we have been addressing last time. The function is given as 3x plus 3 1 minus 2 2. Again, the function here is the function here. We miss it, this f of x. Okay, f of x is this as a piecewise continuous function, so that you can easily find the Fourier series expansion like we did in the previous section. So we proceed to our today's section, the Fourier cosine and sine series. Basically, identification of even and odd function is the most crucial in nature. In order to simplify the computation of the Fourier series of many functions encountered in practice, we often exploited symmetry arguments as even and odd function. We have the function f is even. That's to bear in mind what even and odd function is. I think you have been already familiarized with in lower grades even and odd category of a function. So that we have an even function is if f of minus x is f of x, and f is said to be odd function if f of minus x is minus of f of x. Let's say the function f of x is x squared. This function is even because f of minus x is minus x squared, so that mean minus x squared mean duplication twice of minus x times minus x. You mean we have minus x times minus x, then this is x squared. Good. So this return it back to the original function f of x, so that f of minus x is f of x. So this means the function is even. When you come to f of x is x cubed, we look at for f of minus x. That means in place of x we replace minus x, then cubed, duplication 3 times, you mean minus x times minus x times minus x. So this means minus, we have minus 3 minuses, then minus is plus, then minus x times x is x squared, then times x is x cubed. So this means minus x cubed mean x cubed with the f of x. So f of x, that means f of minus x is minus of f of x. You mean the function is odd function. Naturally, cos x is even function, sine x is an odd function. Sorry. But no, of course, many functions are neither even nor odd function. Clearly, the graph of even function is symmetric with y-axis. Okay, that's the left and right halves of the graph are mirror images of each other. It must cross the y-axis. So that it's just symmetric with the y-axis if the function is x squared, so that my function maybe it looks like this form. Okay, so symmetric with the y-axis, so this is x squared function. Graphically crosses the y-axis, and if we have an odd function, then it's just symmetric with the origin. You may consider the function like okay, this form, and x squared b and xy here, the x and y axis. Clearly these are functions are symmetric with the origin. That it must pass through the origin, you mean? Must pass through the origin. Besides, we have rules of even times even is even function, even times odd is odd times odd is even function. Okay, even function, even times even. Let's say we have x squared is an even function, x4 is an even function. We are not saying an even number or odd number. Okay, we are dealing with the even and odd functions. So x squared, x4 is x6. x6 is an even, so this is even function, again even function, so we get an even function here. Even and odd function is odd. Let's say cos x is an even function. Okay, all right, and an odd function, let's say this is 1 over cos x. Cos x is 1 over cos x is an even function, then times sine x. This is odd, this is odd, this is even. So sine x times 1 over cos x means tan x. So this tan x is odd function. Okay, odd function. Even times odd is odd. Odd times odd, you mean like x times x cubed. So this is x4 is even. We have odd function. Multiplication is an even function, you mean. I think it's pretty easy to understand. That's for the sake of remembrance. In line with that, we have also properties of an odd and even function. From minus L to L of odd function dx is 0. If we like to integrate the even and odd functions over symmetric interval from minus L to L of odd function, and if the integrand is odd, then integration over minus L to L is 0. Okay, so without mnemonic device, if you have minus 2 to 2 of odd function x dx, so this is 0. Okay, because this is odd, again we integrate. Had it been this is 0 or 1, different from the minus 2, it could not be 0. Okay, it could not be 0, but it should be on the symmetric interval. It should be on minus L to L, from minus L to L, not from L to L or any forms. Obviously on L to L is 0. So this, when you come up with the ordinary form, we have x squared over 2 on minus 2 to 2, x squared over 2, that means half. X at 2 is 4, then x at 2 is 2, then squaring is 4 minus x at minus 2 is minus 2, then minus 2 square is 4. So half 4 minus 4 is 0. That means any form of minus L to L of odd function and integration is 0, whereas when you come to even function, then it just equals 2 with 2 y's from 0 to L. That simplifies our task, you mean. Let's say minus 2, the same form, x squared is even dx. This is 2y from 0 to 2x squared then dx. Now let's compute individuals. X squared dx integration is x cubed over 3 at minus 2 then 2. Then we will look at and compare which one is very simple. Then x3 over 3, then at 0 again at 2. Here we have 1 over 3, then x at 2 is 2, then 8, minus x at minus 2 is minus 2, then minus to the power of 3 is minus 8, then it becomes plus 8. Okay, again we have 2 over 3, then x at 2 is 2, then 8, minus x at 0 is 0, then 0 cubed is 0. So 8 plus 8 is 16 over 3. 16 over 3 in the left side. Again, 8 minus 0 is 8, times 2 is 16 over 3 on the right side. Okay, they are equal. But the right side expression is simple. Beside this, we have again a function to be extended. Let f be defined on 0L. Assume f is defined on 0L. Then the even extension of f of x is defined as here, fe. It can be extended in only one way, either to the even and odd function. If f is defined in 1/2 on 0 to L, then it can be extended in only one way, either to the even extension or odd extension. In the previous, we have seen that the odd and even functions, what even and odd function, and the product of even you can have also odd plus odd is odd, even plus even is even, but the sum of even and odd functions can be anything. Okay, sum of even and odd function can be even or odd or neither. Okay, so we are going to extend in either to even or odd function. So the even extension of f of x is defined. We need to extend to minus LL. So though the function is defined on 0L, possibly, we can extend to minus L to L as an even extension or odd extension. When you come to the even extension, we have fe, where you denote that even extension fe of x. The even extension of f is f of x itself in this interval, whereas f of minus x in minus L less than x less than 0 need not be defined as 0. It's not necessary. When you come to the odd extension, the even extension, that's just a mirror image. Here is a mirror image. The odd extension of f of x is defined as fo, the subscript, to denote the odd extension you mean, and this interval itself, whereas to the left side from 0 to minus L is minus of f of minus x. Again, this is the image through the origin, where this is the mirror image. This function is a mirror image, the image through the origin. So keeping this in mind, we can define the Fourier cosine and sine series representation. Let f be an even 3L periodic function. Then the Fourier series is defined as f of x a naught plus an cos n pi x over L, where a naught and an is here. Okay. Good. Let me adjust it. Okay. All right, let f be an even to L periodic function, then the Fourier series is defined as f of x is a naught and indexed from 1 up to infinity, and cosine pi x the summation, where a naught is 1 over L from 0 to L f of x dx, and is 2 over L from 0 to L f of x cosine pi x over L dx. And it's called Fourier cosine series because we have a cosine term. Because Fourier series, you mean a series of cosine and sine terms representing a periodic function in terms of cosine and sine terms we mean. That's intuitively we define. So that if we have a cosine terms only appears in the representation, we call Fourier cosine series. Fourier cosine series. Okay, Fourier cosine series. This is just reduced from the assumption of what Fourier series you may define last time. The Fourier series of the function f of x. Because last time we make, let me show you a bit about the derivation. Last time we defined Fourier series of periodic function defined on minus L to L is given by a naught and cosine pi x over L plus bn sine n pi x over L. So this will be the definition, the fully Fourier series expansion. But identifying even or odd function would help us to minimize the task of computation in Fourier series. Where a naught plus, you mean from the definition what a naught is from the fully Fourier series expansion 1 over 2L from minus L to L the function f of x dx. So if the function is even, or if we are looking to the even extension, this means twice from 0 to L, like we discussed before the even function. We have even function here. This even function is twice from 0 to L. That's why twice this can be reduces to twice 2 over 3L from 0 to L, then f of x dx. You mean this would be equals to twice from 0 to L, twice from 0 to L, but we have 1 over 2L, so this will be cancelled, remains with 1 over L from 0 to L, then the function f of x dx. You mean that's a naught in the new form when you identify f is even function. Clearly if f is even function, n is 1 over L, we have seen 1 over L from minus L to L, the functions and cosine of n pi x over L. This is formula. F is even, cosine function is naturally even function, even times even is even function, the entire product. So we have 1 over L, then from minus L to L of even function mean twice from 0 to L of f of x cosine of n pi x over L, then dx. You mean, okay, so 2 over L. So that's derived from the, where bn is in this case is 0. Bn is 0, no need to compute what bn in if the function is even, if or you likely extend it to a even function. Again, this will be resulted from the formula, because once you have formed as bn, you mean the formula is 1 over L from minus L to L, the function sine of n pi x over L dx. This means 1 over L. This function is even. We assume sine function is natural odd function. Even times odd from the previous rules is odd. So from minus L to L of odd function is 0. Okay, from minus L to L of an odd function dx is 0. That's why 1 over L times 0 is 0. So Bn is 0. So no need to find what Bn. Simply you set Bn is equal to 0 after you identify the function is even function. Okay. Similarly, you can have also Fourier sine series terms. So if the function is have no Bn, you mean we have no cosine term. I mean sine term in the previous, because you clearly make that if Bn is 0, we have cosine terms only. That's why name it as Fourier cosine series. Okay, Fourier cosine series. Again, if the function is odd function, for odd function we have f be an odd function, or if you like to extend, if the function f is defined on 0L, then you can extend to odd extension in one way, either to even and odd. Likely, we have also Fourier sine series, series representation. So if f is an odd function, only Bn is existed, a0 and an is 0. a0 is 0. Okay, so setting a0 and an as 0 because f is odd function. So let's say a0 in the previous 1 over 2L from minus L to L f of x dx, you mean f is odd, mean from minus L to L of odd function is 0. That's why a0 is 0, you mean. Whereas Bn is twice over L, so you can develop the derivation like we did in the Fourier cosine series representation, so that you can find or develop the idea of Fourier cosine and sine series representation through the instance. Okay, this is the example. Find the Fourier series of f of x cos pi x on minus half and half. The function f of x is cos pi x. Cos pi x is even function, so we have Fourier cosine series. Okay, the representation is Fourier cosine series. Fourier cosine series representation. We have Fourier cosine series due to the even function, so that we set Bn is 0. Bn is 0. No need to compute Bn. Just perishing your time when you apply the direct formula for Bn. Ultimately you gain 0. That's why not to perish your time, you simply set Bn is equal to 0 after you identify that the function is even. So we are looking only to compute a0 and an. Here L is half of the symmetric. The function defined on minus L on minus half and half, you mean the length of the interval is 1. You take from minus half to half, you mean 1. So 2L is 1 unit. That's the period. Every 1 unit, in every 1 unit, the function duplicates itself, you mean. So f of x plus 1, you mean f of x. So the function is even here. So we compute a0 and a. With the help of the new formula, a0 is 1 over L from 0 to L f of x dx. The function is cos pi x, so from 0 to half cos pi x, you mean integration of this via substitution technique, that is cos pi x. All right. So we got sine pi x over pi, letting pi x is u, du is pi dx. So we got this. So at half, again at 0, sine pi at x equals half is sine pi over 2. At x equals 0 is sine 0. sorry. So sine pi over 2 is 1, sine 0 is 0. We get 2 over pi 1 minus 0 is 2 over pi. That's a naught. I think it's extremely elementary to compute. That's just a matter of integration. So that you have to revise the techniques of integration to bridge the gap, because we skip a big chunk of the work, especially in integration. Again, a naught is 2 over L from 0 to L f of x cos n pi x over L. From L is half. So 2 over half mean 2 over half. That is 4. Again, from 0 to half. Cosine of pi x, cosine of 2n pi x. Because this is L is half. Half you mean, then you just reciprocate it to the numerator, you get 2n pi x dx. So we have cos, this is A, cosine of B, cos A, cos B. You remember from the previous discussion, cos A, cos B mean cos A, cos B is cos A plus B, cos A minus B over 2. Okay, this is cos A plus B, cos A minus B over 2. So A plus B mean pi x plus pi x. That mean, let me tell you, A plus B mean pi x plus 2n pi x. Pi x is common, so we have 1 plus 2n, then pi x. Okay, so that's A, cos of A plus B. Similarly, A minus B mean 1 minus 2n pi x, 1 minus 2n pi x dx. Now we apply termwise integration. Cosine of 1 plus 2n pi x over 2. 2 can be moved out, that's why it becomes 2 here. Now we look at again cosine of 1 plus 2n pi x integration. You mean letting 1 plus 2n pi x is u du mean 1 plus 2n pi dx. So dx you mean du over 1 plus 2n then pi. That's why we move out pi here, 2 over pi. So sine of integration of cosine of u, you mean sine u. Back substitution 1 plus 2n. Again dx, du over 1 plus 2n is here. Similarly, you can also work out this via the substitution, sine 1 minus 2n pi x over 1 minus 2n. That's very simple. So that you go ahead with assigning specific value at half, again at 0. At half, again at 0. At 0, if x is 0 here, sine of 0 we have. Again, if x is 0, we have sine 0. So we ignore at 0. We only work out on half. If x is half, you mean. If x is half, we have sine of 1 plus 2n, then pi over 2, because we have half. Half times 1 is half pi. Then you just distribute it. If this is half, you mean. Okay, if this is half. Basically, for the time being, we ignore at 0. That's why at half you mean half of pi times this, pi over 2 minus n. Again, pi over 2 plus n. Okay, this is it. So sine of pi over 2 plus n pi plus sine of pi over 2 minus n pi. 1 plus 2n here, 1 minus 2n here. So sine pi over 2 plus n pi is, you can construct the trig identity. Sine pi over 2 plus or minus np is this. Sine pi over 2 plus np means sine pi over 2 cosine np plus cosine pi over 2 sine np. Again, sine pi over 2 is 1, cosine pi is minus 1 the power of n. Okay. Again, cos pi over 2 is 0, sine n pi is 0. So we ignore this for any plus or minus. whether it's sine pi over 2 minus n pi, whether sine pi over 2 plus n pi. So we have minus 1, sine pi over 2 is 1, this is 1, so 1 times minus 1 the power of n is minus 1 the power of n. So we have minus 1 the power of n in here, again minus 1 the power of n in here, move out as a common factor, remains with 1 over plus 2n plus 1 over 1 minus 3n. You just cross multiplication to get this common denominator here. We multiply this by this, is gives this 1 minus 2n, 1 plus 2n, 2n minus 2n is dead, 1 plus 1 is 2, 2 times 2. We have an is this form. Hence, the Fourier series is this, that is the Fourier cosine series. You mean only cosine terms appears in this case. So that we have cosine terms only appear in the Fourier series expansion. That's what we call Fourier cosine series expansion. Bn is 0. We need not to perish our time. We simply just setting Bn is equals 0 in finding the Fourier series of even function Bn is equals 0. If we have odd function, we set a0 and n is equals to 0. You simply compute Bn using the formula 2 over L from 0 to L f of x, then sine of n pi x over L, then dx, you mean, which is very simple. It just simplifies our task of computation, especially after you identify even and odd function. But when you come to the functions that defined on half interval or on 0 L, let's say that find the Fourier sine series of f of x equals to L, where x is in 0 pi, not on the symmetric interval. So here L is equals to pi. So we need to assume that this could be extended in an odd extension here. We need to make odd extension. So in between 0 to pi, so that we assume for Fourier sine series a0 and n is 0, you look only for Bn is equals to this formula. Bn is this, sine n pi x over L. L is pi here, function is 1, again L is pi, 2 over pi from 0 to pi 1 sine nx. Sine nx is cosine x dx. So this the Bn is this form, because when cosine x at pi is cosine pi minus 1, then at 0 you mean minus 1, because if you make at pi is cos n pi, cos nx at pi is cos n pi minus cos 0. That's why it remains with this form. Okay, so hence the Fourier sine series is here, only sine terms are assuming, even you can